So yesterday we started cross-sectional volume, okay? So today we're going to practice cross-sectional volume, but when the cross-sections are perpendicular to the y-axis. So yesterday we basically focused on if they were perpendicular to the x. So they give us this region. It's bounded by y equals 9, y equals x squared, and it asks us to find the volume of the figure if the bases are perpendicular to the y-axis, okay? So this is our two-dimensional area that we're going to be dealing with. And then we're going to create volume by taking squares and actually putting them in very similar to this. Okay, so this one could be, this is a square here, or we could use this one here, or this one here like this. And we're creating this kind of three-dimensional volume that's going to look something like this. Okay, and they're going to be coming out of off the board. So like you can't really, I mean, it does actually look a little more 3D when I do it like this than I was yesterday. So you can kind of see what's going on. Okay, but as soon as you see that the cross sections are perpendicular to the y-axis, you know you're using this equation. If my board will work, the integral from a to b of a, hold on, my pen's not working. I think it's running out of ink. A y dy. So we know we're using this equation right here. Okay? Now, a to the y, since we're using squares, basically the equation is b squared, because that's the area of squares with the base of b. Okay? And that's what we talked about yesterday. So the base of my square is from here to here. Okay? So we need to find the equation for b, the base itself. Now, this problem actually brings us back and is similar to a problem that we worked when we were doing optimization. Okay? When we did optimization, there was a problem where we had a rectangle that was inscribed inside of a parabola, and we had to find the maximum area that rectangle could have based on the equation from the parabola. So this is very, very similar. If it were two different functions, I would just do the right function, the right side minus the left side. But since I'm hitting the same function, that doesn't work, because then it would be x squared minus x squared and it would be 0. And obviously the length can't be 0. So we have to come up with a different way of finding this equation. So if we think back to then, if I look at just this coordinate right here, this is the coordinate x, y. Okay? Or this coordinate here. If you want to think about any of these corners, will hit right there at x, y. Okay? I'm not talking about specifically this corner and trying to measure this one. I'm trying to find an equation for any one of these. Because when we plot a coordinate, basically we go this far in the x, this is our change in x, to here, and then we go from here to here in the y. So this distance right here, from here to the corner, that is my x distance for that coordinate. Which means this base, any of these bases, this distance from here to here is x. Which means the entire base length is going to be 2x. Okay? Now that's still problematic because my area equation has to be in terms of y. So what I have to do here is I have to go back up here, and I know what y is equal to. I need to know what x is equal to. And in this case, x is equal to the square root of y. Technically, plus or minus the square root of y, but we're just going to use the positive side. Okay? So that changes my base equation to 2 square root of y, which also makes my a of y equal to 2 square root of y squared. Okay? So now we got part of my integral set up already. So it's going to be the integral, and the area equation is 2 square root of y squared dy. Now I got to find my limits of integration. And this is the part that always trips up my students, is that they want us to use the x values and say the volume starts here and ends here, and the x. But since we're creating an integral in terms of y, the integration limits have to be in terms of y, and my volume starts here at 0 and ends at 9. Okay. Also think about it as a prism. Your height, if you cut through the prism at any height, you should get the same shape. If I cut through this way in the x direction, if I cut through here, I'm not going to get the same shape every single time. And it's not going to be a square. So just think about it in that way. So that means my integration limits are from 0 to 9. And now we're just evaluating a definite integral. This is the easy part. So you square your 2 square root of y, and you get from 0 to 9 for y dy. Take the antiderivative, you get 2y squared, and you're going to evaluate it from 0 to 9, which means this is 2 times 81 minus 0, which is 162. And that's our answer. That is the volume. Now, relating it back to what we did yesterday, if you watch the notes from yesterday, we basically did the same problem. The difference is we only did from here to here. We created the volume using this rectangle. And if you notice that this is 1/4 of the new area that we're using. And if you look at our answers, if you take the 81 divided by 2 answer from yesterday and you multiply it by 4, there's that 4 right there.